So they go in here in all variety of orientations, and then they come out and they're either plus Z or minus Z. Yes?
When you say that they come in all kinds of orientations, is that like, would it be possible to know what orientation they went in with?
Not any individual spin, no. Okay, and so this h bar over 2, so SZ hat on a Z plus electron will give us plus h bar over 2 Z plus, and if I measure SZ minus, I will get minus h bar over 2 Z minus. So these ones have a positive spin angular momentum, the spin up ones, and these ones have a negative spin angular momentum. Okay, so those are an important set of equations. And now I want to give you 3 different experiments. So now this was an SGZ apparatus. So if we had, before I go into the experiments, if we had an SGX apparatus, and I sent in a bunch of electrons unpolarized, so if this is an SGX apparatus, so that just means I'm changing the orientation of my magnet in there from the Z direction to the X direction, say. Then I will get out an X plus and an X minus, what we'll call X plus and X minus polarized electrons. Okay, and again, if we measure, so we'll have a corresponding measurement for our apparatus here, S of X, and if that operates on an X plus electron, it gives us back plus H bar over 2 X plus and S of X operating on an X minus polarized electron will give you minus H bar over 2 times X minus. Okay, so that's just, because Z and X are just labels, right? Z and X don't really mean anything, they're just labels. So it doesn't, if your X might be my Z or something like that. So the outcome of the experiment has to be the same. If all of the things are equal, namely we just have an unpolarized beam that goes in. Okay, so now, these are actual experiments that you can do. This is the Stern-Gerlach experiment. Now we can string a couple of these Stern-Gerlach experiments together, and we can learn an awful lot about that. So let's see what some experiments are that will tell us a great deal of things. So let's consider now 3 experiments with SG apparati. I'm not sure if that's the plural of apparatus. Is it apparatuses or apparatuses?
It could be either, depending on the root, I guess.
Okay. All right, so let's do, let's call this one A.
Apparatuses.
Apparatuses, is it?
No, it's apparatus.
Is it?
Apparatus and apparatuses, both correct, both fine.
Okay, I'm just half joking because I don't know what it is.
Okay.
Okay, so let's say we have this now I'm gonna be a little bit more specific. We'll go into an SGZ apparatus. And we'll have these two beams that come out, the plus beam, and then the minus beam, we're gonna put a beam stop. Okay, we're just gonna block that beam. So all of the Z minus electrons are just gonna, they're just gonna hit a block. And we're going to assume that there are N0 of these, the number. You could consider this as a number per second or something like that, that's fine, or just the total number that you count over a specific time period. And what we're gonna do is we're gonna put them right back into another SGZ apparatus.
The plural is apparatus.
Is it?
Yeah, it's just
Okay.
apparatus. Or apparatuses, but never apparati.
Okay. All right. So let's take our apparatuses. We'll take the plus beam out. So this is our Z plus beam, and we're gonna put it right back into another SGZ. And what do we get out this time? Well, it's a polarized beam already, right? So what do you think we get?
It should be positive, or it should be spin up.
Okay, but how many of these do I get spin up?
You would expect when they all be spin up.
Yeah, would it be 100%?
Okay, good, that's just N0, and we get 0 down here, right? Okay, that measurement tells us something, which I'll get to in a moment, but that's it, so. They all come back out, whatever I put in. If I already measured it with a Z apparatus, and then I put it back into a Z apparatus, I just get the same thing back out. Now, on B, I'm going to put an SGZ apparatus. We're going to have N0 come out in the plus beam, and then we'll put a beam stop again on the minus part, the minus beam. And now we'll put it into an SGX apparatus. Okay, so what are the numbers that we get for the, what do you guess the numbers are that we get for the plus and minus beams?
50-50? Should be 1/2 N0 for both.
Anybody else?
Is it 100% negative?
So we're only allowing the spin up ones to go into the
Where do you get that?
apparatus, right?
Yes.
So
We're only allowing the spin Z plus, these are Z plus,
Oh.
Right.
Those
This is
Z
a
plus
Z.
is going into the X box.
going into an Xbox.
So yeah, it would be 50/50.
Okay, anybody else? All right, good, yeah, I mean, it's 50-50. It's not obvious.
Well, I guess my thought was just because the beam, the polarizing force is orthogonal to the original polarization, so there shouldn't be a.
That's good intuition. Okay, so that's A and B, and then let's do C, where we go into a Z apparatus. Let me make this a little bigger. So we'll take N0 of the plus beam, we'll put it into a SGZ apparatus. Sorry, an SGX apparatus, and then now we'll take, we'll put a beam stop on the SGX minus. So this beam here is just the X plus beam. And we want to put that back into an SGZ apparatus. Okay, so now what should we get? Anybody?
I have two
It
opposing
should
ones.
be 50/50.
Okay, 50-50.
And I think they would all, I think it's all positive. I know it's one, I know it's something counterintuitive, but I don't know which intuition is the one that's wrong.
I think it would be 50% spin up and 50% spin out.
To be an N zero. Yeah, N zero.
Right, it'll be a 50-50 split of the N
So
over two.
in over 4?
Yeah. And that's consistent with this experiment, right? Because we went in with just a Z plus, and then it got split when we went to an orthogonal measurement. And so it's the same thing. This is just a bunch of X plus going in, and so the Z splits it again. But that tells us something interesting. It tells us that a measurement changes the state. Okay, so these are all real experiments that you can do. So what do we learn? So on A, if we measure the state once, so a repeated measurement, will yield the same result. Okay, now, what can we learn? What can we learn from the experiment B? So we have a pure Z plus beam that goes into a 50-50 mixture of X plus and X minus. Okay, so I'm going to write an equation, and I'll make sure that it will be normalized. We'll talk about that in just a second again. Okay, what this equation says is that these are two states. I have an equal mixture of them because the coefficient in front of both of them is the same. And that is somehow equal to Z, because when Z goes in, it gets split into these two states. Okay? This is an interesting thing to be able to write down from an experiment, because this is an expression in linear algebra.
And so the coefficient represents, I guess, the outcomes, which was the N naught over 2 for B and the N naught over 4 for C.
Yes. And I'll explain how we actually get to this 1 over square root 2 in just a minute.
Okay.
But being equal, that just means equal numbers. So in this particular case. Okay. All right, so that's B. And then on C, what this means is that some measurements some measurements, for example, this SX hat, or sorry, SG X apparatus, will destroy the information that this was a Z plus beam, right? And right, so it's in the Z plus state. I polarized the beam by selecting this beam from this apparatus. But then when we put the SGX apparatus in here, it mixed them again. And then, so I'm taking, if I'm just taking like the X plus beam, or actually this, I should be talking this experiment kind of not that one, sorry. If you just look at the second half of this, second half of the experiment here. So in this case, it's an X plus beam, it goes into a SGZ apparatus, and then it gets split into the two beams. So I lose information about that. I mean, it's, you know, this apparatus destroys the Z plus character of the beam. Okay, and so we call these, so we say that SZ hat and SX hat are non-commuting. Okay, so they can't, they're not complementary in that sense. Okay, so now let's get to the numbers here and probabilities. So in quantum mechanics, measurements when you make a measurement in quantum mechanics, you have to think of the answers that you get when you make measurements on systems in terms of an ensemble of experiments. One measurement can't tell you all of the information you need, okay? So I can send, for example, one electron, and I have no idea what its polarization is. I can send one electron by itself through an SGZ apparatus, and I'll get up or down. But if I have my collection of electrons over here, I can't tell you what the state of those electrons is from the one measurement. I have to send many electrons through the apparatus and then count to find out how many I have, and that tells me something more about the state. So let me see how I want to say this in a second here. Let me stop here. Let me show you some. Okay, so if we're talking about an electron, then we want to measure the spin state of the electron. We're just going to get spin up or spin down. But that really doesn't tell us what that state was beforehand. What we need to do is to make measurements on a bunch of identical systems and collect some statistics about the results. So I will get some results that are, I'll get so many spin up and I'll get so many spin down. And then I can have a little bit more information about the state of the system of those electrons.
You'd be able to tell if something was like partially polarized because it would have more than one or the other.
Sure.
Yeah.
But even then, that's not, the amount of information in a quantum state is still a lot larger than that. So even if you had the numbers, that still doesn't tell you everything that there is to know about the state. Okay, and I'll explain what I mean by that in a little bit, but it's, we can actually illustrate this a little bit later for, this is why quantum computing is so powerful. Because a single qubit has more than up or down, right? In classical computing, you just have, you have a bit that's 1 or 0, but in quantum mechanics, you have a superposition of states and of spin up and spin down, and you have complex coefficients. So you have a lot more degrees of freedom in there. And that's what makes that's what makes the information content in, a qubit or so, a set of qubits so much larger than you can get in any kind of a classical computer. Okay, so let's talk now about what it means to actually measure the numbers that come out here, because we want to have a probability, for example. What is the probability so just speaking about the Z apparatus, what's the probability for the outcome of SGZ to be plus or minus? Well, if we have so many N0 going into our apparatus, and we have let's say A over N0 and B over N0, then the total number has to be equal to okay, we'll do this. Just call it A and B. We need A plus B to be equal to N0. That's just a constraint. If we have N going in, this is the number coming out. And so the probability we can say PZ plus then would be A over N0, and PZ minus would be B over N0. Okay? So this is just numbers, right? A is some number coming out, and I divide it by N0. So if A were equal to N0, then that means this was a polarized beam coming in, and right, okay? Now, let's also take another look at what I need to introduce some new notation. Okay, so so in quantum mechanics, we describe processes are described as having an amplitude and a probability. Okay, and an amplitude is just a complex thing that can, can cause interference. Okay, and probabilities are just, probabilities have to be real numbers. Between 0 and 1. Okay, so if a process is not going to happen, then it's got a probability of 0, and if it's going to happen with certainty, then it will have a probability of 1. But the amplitudes are complex numbers; they're sort of intermediate to the description here. But the square of an amplitude gives you a probability. This is the complex square, or the magnitude squared. Okay, so now let's go back to this equation here. No, well, let's go back to this experiment. I'm sorry. The other thing that I need to mention is that when we describe a process, let's see. Before I do that, let me go ahead and let's go over here. Okay, let's go back to the first experiment. And let's look at this part of the experiment. We have a Z plus beam going into an SG-Z apparatus, and then it comes out as Z plus. And if there are N0 here, we'll just get N0 out. Okay, so we can we can write the amplitude for that process like this, where this is the initial state and this is the final state. Okay? And so the probability 1 means the following. So magnitude squared is equal to 1, because that's the probability. Okay, so this takes a little bit of getting used to, that this is how you write things or how you think about things. So now we're gonna have to work a little bit on what these amplitudes are. Okay, so this is an amplitude. To go from Z plus to Z plus. Yes?
So in this Stern-Gerlach experiment,
Mhm.
what if the input electrons, right, from an oven or whatever, are unpolarized, then how would you write that in the initial state?
Okay, we'll do that next. It's B over there, it's part B though.
Oh, right.
Well, I mean, a Z beam is an unpolarized X beam,
Oh, I see.
because there's 50-50.
Right.
But yeah, so an unpolarized Z beam would be an equal mixture of Z plus and Z minus.
So the bracket, the Dirac, whatever the.
Bracket, yeah.
Doesn't that mean it's already like a square because it's a conjugate times, or it's a complex number times its conjugate? Or is that what that bottom thing is? Is that's how you calculate the magnitude of a complex vector?
Well, the inner product, which is the Dirac bracket here, this is gonna be in general just a complex number,
Okay,
okay? And that complex number is called the amplitude.
okay,
But when we want to get want to get a real number out of it, then we have to take the complex magnitude squared.
okay, so that's a complex inner product, and then you take the magnitude, okay.
Yeah.
Got it.
Does that make sense? Okay. Okay, so, now let's look at the, if we consider the experiment B now. Okay. Oh, I should. This experiment, also, from this experiment, we have if I come in as a Z plus, I don't get anything as a Z minus, so Z plus, Z minus equals 0. Okay, and this also means that Z plus, we can take to be 1. Okay. So there's a couple of things we learned then. Z plus and Z minus, if we think of them as vectors,
They're orthogonal.
they're orthogonal. The inner product is 0. So we can use them as basis states, okay? So now, obviously we must have then x plus is equal to 1, and x plus x minus is equal to 0 for an independent SX apparatus, SGX. Okay, so now if I look at this experiment here, I have x plus as an outcome, the probability. So I know that x plus is coming out, but I had z plus going in, a polarized beam of z plus, and I know that I get half in each channel here, or half in that particular channel, so this squared has to equal half. So this is from the experiment, I know this. So the probability, this is the probability. And then we also know that z plus x minus squared also has to equal a half. Okay, so these are some things that this is from the experiment, this is what we know. Yes?
So, over here you said the final state was on the left and the initial state was on the right,
Yes.
but this is experiment B, where the final state I thought
Oh, did I
was
switch it? I'm
X.
sorry. This should be the initial state, sorry, that's a Z,
Okay.
yeah.
Okay,
Thank you.
good.
Yeah, thanks for catching that. Okay, any other questions? Okay, now we can do this, now we can look at this experiment, so this is a Z plus, for example, here. So experiment C tells us now let's see, I've got to start here with a Z plus, and then I'm going through an X plus, and then now the way you chain, the way that this occurs here is through this process, X plus to Z plus. Okay, so this is a process where I go from
Is that the wrong
did I do
direction
this
again?
Did I do it
Yeah.
backwards again? I keep doing it backwards. I don't know why I keep doing that. All right.
To be fair, I don't think that the rock notation's that
Z plus,
actually
X
intuitive.
plus. Actually, it's the same thing when you write it down, so it didn't really matter, but okay. Okay, so there's an amplitude, that's the amplitude. And then if we take the magnitude squared, this has to be a quarter.
So the directions Z and X are orthogonal to each other. But
No,
the spin.
Z and X are not orthogonal.
The directions next.
Well, the physical direction of the apparatus.
That's where it gets.
But this says that Z, if I'm thinking of it as a unit vector in my spin space, is not orthogonal.
We're not in real space, we're in spin space now.
Right. Yeah. Does that make sense? That's confusing. I know.
No, it doesn't make sense, but I'll accept it.
It'll start to make sense after a while. Okay. Other questions? So let me reiterate this point down here again. So let's just do an example with, so we can do another example here where I'll just put, let's call this A, and then M1, M2, B.
I think this is on the homework.
Huh?
So I think this is on the homework.
It is. So, this sequence shows how you go from, if I have two amplitudes, right? I've got an amplitude for this Z plus to go to this X plus, that's here. And then I've got an amplitude for this X plus to go to this Z plus, and that's here. And those are multiplied because it's part of the chain. But in this case, I'm going to have two paths. So there's two separate paths. And in this case, so if we want to go, if we're going to from left to right here, then I would write the amplitude. The amplitude for the process is, I go from A to M1, and then I would go from M1 to B. Okay, that's the top path. But the rule in quantum mechanics is if there's more than one process possibility here, you have to add them at the amplitude stage. So that means we'll have the second process with M2 added to the first process. So this is the total amplitude. So we must add and you have to add those at the amplitude stage, and this is what it's the fact that we add these amplitudes and then we take the magnitude squared of the amplitude to get the probability. That's this is where you'll get interference. It's during where you take the complex square of the amplitude. That's where interference occurs. And so
You're
that's an
saying interference
important.
occurs when you do the complex magnitude? Say that, I guess, the last part again.
Yeah, so this is if this is, let's see, I should call this. Let's call it Z or something. That's the total amplitude. Then Z star Z is the probability. And so it's when you take the complex conjugate of a complex number, right? You change the sign and the exponent for where the I is, and that allows it to knock off positive exponent. Right. So that's the origin of the interference. Yeah.
So when you take that complex magnitude, do you put the magnitude over like the entire thing, or do you have to do each one individually and then the plus goes in between the two magnitudes? Like, does
this is a whole,
Okay,
these are,
magnitude the whole thing.
yeah, you have to complex, yeah, so that's like, you know, you have four complex numbers there, right? C1, C2 plus C3, C4. So you have to complex conjugate that, and then,
Gotcha. Okay.
So,
Yeah.
I'm not really sure with that equation, what there has to do with your diagram.
this equation?
Yeah, I don't understand what this equation is.
Okay, so we've got path one and path two. So if we think of the amplitude, to go from A to M1, that's this part. And then I'm going from M1 to B, that's this part. But now I have
Okay, I understand.
now it's a completely separate path, so I have to add the amplitude.
Okay, I understand. That's what you mean here, right, intermediate states. Okay,
Yes.
okay, I understand.
Already 4:30, okay.
So that should equal 1, right?
What?
That the magnitude of that equation there, because it has to end up at B. That's something like it has to end up somewhere.
Doesn't have to.
Oh.
That could be another screen, right? I mean,
I guess that's true.
if this is like an electron emitter and here you've got a screen,
Yeah.
you're just asking, what's the probability it ends up at B?
Oh, what's the probability ends up with B? Okay, gotcha.
Right, you're trying to calculate that. So I'm thinking of a two-slit experiment here.
Gotcha. Okay. Makes sense.
And so, okay, good.
Any other questions? Okay, so let's see. So if I want to now just write the general state of an electron, I can write it like this. Okay? Where C1 and C2 are complex numbers. Okay? So now we're talking about having a lot of freedom in here. Now, I wrote down, for this particular experiment, we wrote down that Z plus is equal to, well, I'm not gonna, let me get back to that in just a minute, sorry. Okay, so now let's consider the following experiment. Where we do nothing. So I've got a single electron now, just zipping by, and I do nothing. So if this is the end state here, and this is the out state, so I've done nothing now, then what should I have? I must have, so we must have, I must have psi equals 1. Right? Because the probability, if I do nothing, if this is the state of the electron and I do absolutely nothing to it, then the state better be the same, if nothing's happening to it. So in that case, we can say that we have the amplitude and also the probability. I could, square this. I must have the same particle. So this just says that the particle must, without anything happening to it, the particle must be in the same state. Okay, and we will use this as a normalization. So this will be a very important convention for us. Okay, so that means, so when we wrote that Z plus was an equal admixture of X plus X minus, then and Z plus equals 1, this is our normalization. We already found this anyway from just intuiting it from the experiment. We can just show this. Okay, so we have this as the ket. Now we can write down the Z. We can write this as a bra, which is just 1 over the square root of 2, and then there's no complex numbers here, so it's very easy to just turn this around. So that's the bra. That's the Z bra, and then we can take the inner product. So Z plus, well, if I take this and then come out, from the left onto this, I'll have a half from each of these terms, and then this X plus will hit this X plus. That'll give me 1. This X plus will hit this X minus, give me 0. And then likewise, this X minus will hit this X plus and give me 1. And, this will give 0 and then this will give 1. Okay? So that's why, that equation that we wrote down here is, that allows us to have our normalization again, and it's also consistent with the probabilities that we measure from an actual experiment. Okay, so let's think about what we did today. So we went over the linear algebra as a review. And, you know, it's very abstract at that stage, but if you didn't know any linear algebra, if nobody knew linear algebra when they did these experiments, they would have discovered linear algebra, right? Because this experiment right here tells you this, and this is a statement in linear algebra. It says that a Z plus electron is an equal admixture of X plus and X minus. Okay, so it's in a superposition of states. So if I polarize an electron in the Z plus direction, I'll always get Z plus out. But if I put it through a Stern-Gerlach X, I'll get a 50-50 mixture. So it means that in some sense, this little Z plus, you know, is going back and forth somehow between X plus and X minus states. So it's in a superposition of those particular states. It's not in one or the other. And most of the things we wrote down today, for example, being able to consider these things as, you know, basis states in a vector space. So thinking of Z plus as a basis state in a vector space and Z minus. Those things they come out of the experiments, the actual experiments. So you're really doing linear algebra experimentally here. So in that sense, I think it's that's what's really fantastic about the Stern-Gerlach apparatus. But you know, let's be a little bit more. You know, this is just an electron with two states. Okay, so we're starting off with as simple as you can get, just a two-state system, and we're going to work our way up to things that have a lot more states later. But there's so much physics in two-state you know, systems here that we'll spend a good portion of the semester just covering spin. Yes?
So back on this other thing, when you did this, when you changed it from the ket to the raw, if that had been the amplitude of 1 over square root of 2 had been a complex number, you would have switched that to the complex conjugate at that stage?
Yes.
Okay.
Yeah, so I can do it over here on this. So if we write, so if I wanted to turn this around and make it a raw vector, then this would be C1 star Z plus C2 star Z minus, yeah. What time do we have?
Okay.
Oh, I've still got some time. Okay, good. All right, let's do this in a little bit more detail. So we can represent we can represent the base states. Z plus and Z minus with matrices. So we can say that Z plus is 1, 0. I'll say that the kets anyways are 1, 0, and 0, 1. Okay. And then the corresponding bras here would be 1, 0. 1. Okay, and so if we write psi is equal to C1 Z plus C2 Z minus, I can write this as, let's say, C1 is 1, 0 plus C2 is 0, 1. So that's just equal to the column vector C1, C2. And then if I take psi, the raw vector, I just turn it sideways and I conjugate. So we have then the relationship, the psi equal, if I take the inner product here and calculate this amplitude, this is the following matrix. It's that matrix multiplication. This is equal to doing the row column multiplication here. We have C1 star C1 plus C2 star C2. So this is just the magnitude of C1 squared plus the magnitude of C2 squared. And so this is a constraint. So if I write you can write it in either this Bra-Ket notation or matrix notation, but we must have the magnitude of C1 squared plus the magnitude of C2 squared is equal to 1. Okay. So this is C1 and C2 are complex numbers. Let's see. Can't use that either. Let's see. Okay, I'll just use. C1 and C2 are complex numbers, and so this relationship means that the magnitude of C1 squared, remember, is just x1 squared plus y1 squared, and then I add plus x2 squared plus y2 squared. This has to equal 1. So these are, x1, y1, x2, and y2 are real. So this is the constraint equation in complex or real numbers. Okay. Okay, so there's a complex number has 2 real degrees of freedom. So there's 4, what looks like 4 degrees of freedom here. Okay. So one quantum bit has, I can solve for one of these in terms of the other 3, so I have 3 degrees of freedom for a single quantum bit. So a qubit has a lot of degrees of freedom. Okay? It's actually an infinite number of degrees of freedom. Because if I bring one of these to the other side, it's the equation of a sphere at some radius. And that's why, this is just a simple qubit. That's why it has so much complexity. So when you're measuring, now, I didn't, is it? When you make a measurement, so we'll talk about this again on Thursday, but, so if this is my qubit or my electron, and I can measure it to be spin up or spin down, when I make the measurement, I send my electron through the apparatus, I only get one answer, right? I just get that it's spin up or spin down. One electron doesn't tell me anything about the coefficients. It just tells me that one of them is non-zero. Okay, but I have all of this freedom in those coefficients. So if I have an ensemble of identically prepared electrons, a whole bunch of them, and I send them one by one through the apparatus, I can at least get the magnitude squared of C1 and C2 because I know they have to add up to the total number of electrons. That probability has to be 1. So I will learn something about the numbers. Okay. Does that, okay, we'll talk about it more, but, you know.